Set 28A, 1 through 4 and 7. So, number 1, find the area under the chi-squared curve with 5 degrees of freedom to the right of 1.6. So down to the bottom of the page, go to 5. Nope, go back a page. 2 pages. And go to 5. 1.61 is going to be 90%. 531. Okay, 9.24 is 10%, and 15.09 is 1%. And all we really care about is, are we bigger than 5% or are we lower than 5%? I don't know why they give us 90 and 50. Maybe we'll find out later. 2. Find the area to the right of 15.09 under the chi-square curve with 10 degrees of freedom. So 15.09 is not on the chart, but it fits between 50 and 10. And it's actually quite close to 10. Okay? So if my chi-squared statistic was 15.09 with 10 degrees of freedom, what would I do? We're between 50 and 10%. I would accept the null. Right? If p is greater than 5%, we accept the null. If p is less than 5%, we reject the null. Okay. 3. Suppose the observed frequency in table 2 had come out as shown in table 4a. Compare the value of chi-squared, the degrees of freedom, and p. What can be inferred? All right, so we're going to compare this. They should all be 10, right? So I need to do 10 minus 5. Then what? I square it, and then divide it by 10. And I'm going to do that with every one of them. So I'm just going to plug them straight into my calculator. 10 minus 5 squared divided by 10. Okay, what's the plus? What's the next one? So 10 minus 7 squared divided by 10. Does it matter if I do 10 minus 7 or 7 minus 10? No, because I'm going to square them. So it doesn't matter. Plus, what's the next one? 17 minus 10 squared divided by 10 plus 16. 16 minus 10 squared divided by 10 plus 8 minus 10 squared divided by 10 plus 7 minus 10 squared divided by 10. Okay, this gives me a chi-squared statistic of 13.2. What was it last time we did this? It was 14 point something. Okay. So now I go to my table. You can either look at the one on A106 or the shortened table on 527. How many degrees of freedom do I have? 5. How do I determine degrees of freedom? It's the number of categories minus 1. When we were doing 2 sample Z tests, or sorry, no, when we were doing t-tests, degrees of freedom was the number of draws minus 1. But when you're doing a chi-squared test, the degrees of freedom is the number of categories minus 1. So 6 minus 1 is 5. I go to 5, and then I go over to 13.2. Where would that be? Between 5 and 1. So we should reject the null and say that there is a statistically significant difference. But it's not highly significant. Right? It's just significant. All right. Do we have to do the same for B, C, and D? Compute what can be inferred. Okay, so we'll answer the question for A. what do we learn about the dice? Meaning it's unfair. We think that the dice is statistically unfair. Okay, check the null. What are we supposed to do with B, C, and D? Oh, I see. Number 4. Suppose the observed frequency in Table 1 had come out as shown in Table 4b. Make a chi-squared test of the null hypothesis that the dice is fair. So I'm going to use the exact same calculations that I did before, but tell me the numbers this time. So 10 minus 9, then the next one. Can I just touch that? No. So this needs to be 11. What's the next one? Wow, this is slow. So 10. And then we'll do 8. And change this 8 to a 12, you said? Okay. And then the last one is 10. Okay. Hit enter. And I get a score of 1. Is that what it says in the back? Yeah. So I look at degrees of freedom equals 5, and my chi-squared statistic is 1. So I go back to my chi-squared chart. 5 degrees of freedom, 1 lands in, it's greater than 90%, which means we accept the null and say the dice is fair. The differences in the chart can be explained by chance variation. There's no statistical difference. No statistically significant difference. All right, and number 7, correct? Oh, lots of questions. One study of grand juries in Alameda County, California compared the demographic characteristics of jurors and the general population to see if the jury panel was representative. The results for age are shown below. The investigators wanted to know whether the 66 jurors were selected at random from the population of Alameda County. Only persons 21 and over are considered. And the county age distribution is known by the Public Health Department of data, or assumed by the, right? Do they know exactly everybody who lives in that town? No, but whatever. A, true or false? To answer the investigator's equation, you should make a z-test on each line in the table. False. Why? There are multiple categories, but what's wrong with testing each category individually? They're dependent. Is your occurrence in the first row affected by your occurrence in the second row? Definitely, because if you're in the first row, you can't be in the second row. So you can't test these ideas separately because they are not independent. They're totally dependent. You could test them separately if you did different samples, right? You went out and you did a sample and you only collected 21 to 40. Then you went out and did another sample and collected 41 to 50. But that's a big pain. You do a lot more work to get the same result. So we can't use a z-test. We have to use a chi-square test. Fill in the blank. The blank test combines information from all of the lines in the table to an overall measure. Options, z or chi-squared. Chi-squared. True or false? The right-hand column in the table gives the observed frequency. Yes, the number of jurors. Okay. Um, the middle column tells you the percentage of those populations. D, fill in the blank. To make the chi-squared test, you need to compute the observed or expected frequency in each age group. Expected. Because we have an expected percentage, but not an expected frequency. Okay? Now answer the investigator's question. So the table 42, 23, 16, 19, and then 5, 9, 19, and 33. Okay, this is the expected percentage. This is the number of jurors. What do we need to do? We need to make a new column that has what? We need to compare the number of jurors to the number of right? I need to do 5 minus something squared over that same something plus 9 minus something squared over that same something. Where do these numbers come from? There, it's the expected number. Do I have the expected number? No, I have. Oh, why are we still recording? We're supposed to be recording. My brain did not come to work with me today. So, so this number tells me the percentage of that particular age group in the county. But that's not what I want. I want how many jurors we would expect to happen in each category. So how do we do that? So 45% of the jurors should be between 21 and 40 because 42% of the population is there. So how many jurors would that be? It would be 42% of the sample. So we should do 42% of 66. 0.42 times 66. That's the total number of jurors, right? Now, it doesn't make sense to use 27.72. So 28. How many in the second group do we expect? 0.23 times 66 is 15.18. Oh yeah, sorry, 15. Told you I didn't come to work today. 0.16 times 66 is 11. And 0.19 times 66 is 13. Okay. So, what do you think? Before we do any calculation, is the jury pool representative? It doesn't look like it, right? We expect every time we have 66 jurors, we would expect 28 of those to be in the 21 to 40 age group, and we only got 6. Okay. Now I need to compute my chi-squared. How am I going to do that? So 28 minus 5 squared divided by 28 plus 15 minus 9 squared divided by 15 plus 11 minus 19 squared divided by 11 plus 13 minus 33 squared divided by 13. Do I expect a high chi-squared value or a low chi-squared value? I expect my chi-squared to be high because I expect my p-value to be very low. So I end up with 57.88. How many degrees of freedom do I have? I have 4 categories, which makes 3 degrees of freedom. So we go back to our table. 4 degrees of freedom, 57.88 is way off the chart. Okay, so we reject the null and we say, hold on, let me see how the question was phrased. The investigators want to know whether the 66 jurors were selected at random. No, there is nothing random about this. Now, you guys are smart. Why might that be the case? If you look at those numbers, why would a disproportionately high number of jurors be in the 61 and over range? They don't got anything else to do, right? One of the questions when you fill out a jury summons questionnaire is, would being on the jury significantly affect your life? And if you have young kids at home, then a lot of times you don't even make it past the registration process. So it used to be they mailed you a card and you filled it out and sent it back in, but now it's online. So if you get a jury summons, you go online and you enter the number that they mail to you, and you answer this questionnaire, and that questionnaire weeds out people who won't be on the jury. And the younger you are, the more likely you are to get weeded out because you have a job, you have kids at home, you have some obligation that prevents you from being on the jury. But those old people, they got nothing better to do. Okay, that was the last one, correct?